7.3 Day 1, we're looking at multivariable linear systems. We're going to use back substitution to solve linear systems in row echelon form, and we're going to use Gaussian elimination to solve systems of linear equations. We're at echelon form in back substitution. The method of elimination can be applied to a system of linear equations in more than two variables. In fact, this method adapts to a computer used for solving linear systems with dozens of variables. When using the method of elimination to solve a system of linear equations, the goal is to rewrite this system in a form to which back substitution can be applied. To see how this works, consider the following two systems of linear equations. So we have here's the systems of three linear equations in three variables. And then this is the equivalent system in row echelon form. And so this is what we're going to be working with. The second system is in row echelon form, which means that it has a stair-step pattern with leading coefficients of 1. So notice here leading coefficients of 1. In comparing the two systems, notice that the row echelon form can readily be solved using back substitution. Okay, so I know we used to solve this in Algebra 2, and so now we're going to rewrite them in this form. And so that really will help us later on when we're trying to solve systems using matrices in Chapter 8. So example 1, we're going to use back substitution in row echelon form in order to solve for x, y, z. So we notice we start with equation 3, and we're just going to plug in z here. So we have y plus 3 times 2 equals 5. So y plus 6 equals 5. Subtract 6 from both sides, so y equals -1. Then we know what z is, we know what y is, so we're going to plug it into equation 1. So x minus 2 times -1 plus 3 times z, which is 2, equals 9, and solve for x. So x plus 2 plus 6 equals 9. So x plus 8 equals 9. Subtract 8 from both sides. So we find that x equals 1. So now that we have that, then we need to write it as an ordered triple. So, of course, x comes first, y, and then z. So this is 1, -1, and 2. So try this example here. Solve the system of linear equations using back substitution. So you should have gotten that y is -3, x is 4, then the ordered triple is 4, -3, 3. So we're going to look at Gaussian elimination. To solve a system that is not in row echelon form, we're going to first convert it to an equivalent system that is in row echelon form by using one or more of the row operations given below. So operations that produce equivalent systems. Each of the following row operations on a system of linear equations produces an equivalent system of linear equations. We could interchange two equations. We'll want to do that when we want, the leading coefficient to be 1, and sometimes it's faster just to exchange the position of equations. We can multiply one of the equations by a non-zero constant, so that could be a whole number, that could be a fraction. Number 3, we're going to add a multiple of one equation to another equation to replace the latter equation. To see how to use row operations, we're going to take another look at the method of elimination as applied to the system of two linear equations. So our goal in this section is to be able to write it in row echelon form. Okay, so I know that we can solve this by, just doing elimination from the previous section, but our goal again is to learn how to rewrite these. So we're going to use row operations to solve a system. So we have 3x minus 2y equals -1 and x minus y equals 0. So we need leading coefficients of 1 in the first equation. So what we're going to do in this case is exchange the equation 1 with equation 2, the position of them. So what I'm saying is that our equation 2, we'll put it on top, and equation 1, we'll put it on the bottom. So now we have x minus y equals 0 because the leading coefficient is 1. Then we have 3x minus 2y equals -1. So you want to leave equation 1 as it is. We want that there. And then we'll want to solve for y in the bottom equation. So we're going to solve for one variable. So In this case, what we're going to do is, in order to, let's get rid of x in this case, so we have y. So I'm going to multiply the top by -3. So -3 to equation 1, I'm going to add it to our new equation 2. So it's just helpful to kind of write the directions. So this is -3x plus 3y equals 0. Then I'm going to add it to 3x minus 2y equals -1. So we get y equals -1. So now we're going to write the system in row echelon form. So we have x minus y equals 0. Then we get y equals -1. So that's the first step. So that's our new system, again, in row echelon form. Now we're going to back substitute in order to solve for x. Now I know this seems really long, but again, it's the process that we are interested in. If we can do it with this, then we can apply it to a system of 3. So let's substitute. We get x minus a -1 equals 0. So x plus 1 equals 0, or x equals -1. So therefore, our answer in this case is -1, -1. So now go ahead and try that in this example here. Solve the system of linear equations. Again, our goal is to rewrite it in row echelon form. Okay, writing in row echelon form, I exchanged equation 1 with equation 2, or equation 2 with equation 1, vice versa. And then I multiplied -2 to equation 1, and then added that to equation 2. Okay, so that's what I'm trying to do. And then, so I multiplied it, -2x minus 4y equals -6, and then 2x plus y equals 3. And then I get 3y equals -3. Now, sometimes you don't want to solve right away. You kind of want to leave it like that. So I just wanted to show you that I left it in that form. And then what I did, in order to isolate the y, is I multiplied by a -1/3 to equation 2. And then when I did that, my new equation 2 is y equals 1. So now it's in that stair-step form. And then I use this to do back substitution, and I found that x is 1. So the answer is 1, 1.